guys.
My name is Paul Bartunik. Just real quick, couple seconds on my background, and then I'll turn it over to Richard. He's going to start the presentation today. I'm a lifelong rep. I've been in the business for over 20 years. Started as a rep. Family was a rep, so back many years. But I spent 10 years as the Vice President of Sales and Marketing for ABB. And Valerie, I'm sorry, am I? Oh, yes. Got it. I spent 10 years as the Vice President of Sales, Marketing, and Application Engineering for ABB. And Richard worked with me at ABB, worked with me before ABB. All the products that you see here, Richard and I were both on the R&D teams that design these products. So if you have questions after our presentation, come on up. We'll talk to you about them, what the design implications were, kind of what some of our challenges were, and the improvements in the technology. And ABB's got great technology, but so do our competitors. So we're not here to talk about brand-specific stuff today. We're just here to talk about the technology. So specific questions, please ask. Challenge us today. If there's things you want to know, let's dig deeper. Let's talk more about it. And we're here for you guys. So I'll turn it over to Rich, and he's going to talk a little bit about the energy savings aspect and how drives save energy.
Hi, I'm Richard Schnorrenberg. Thank you, Valerie, for the introduction. So I've been with mechanical sales for just a couple years now, but before that I did work with Paul at ABB in Milwaukee, where there was a bit more snow than what we have today. I worked there for 8 years. Prior to that, I was a ABB guy here in Kansas City, so I'm a Kansas City guy, and I'm glad I came back this way so I don't have to deal with all the snow that they do now. So I was a senior application engineer at ABB and then a regional sales manager. And like Paul said, we pretty much can answer all the questions you'd want to know about this drive or pretty much any drive out there. So most of the stuff we're going to do today is going to be generic in terms of VFD related stuff. And I want it to be an open conversation, so if anything piques your interest while I'm talking about it, please stop and raise your hand, and I'll happily dive into the questions you got there. It's way more fun for me if I'm answering the questions you want to do, and probably better for you, rather than just listening to me spiel, if we're actually interacting and doing what you'd like to do instead of just what I've got up here on the screen as soon as I hit this button. Okay, so this is Design Mechanicals University, DMI University. This is the VFD Roundtable discussion. I've got a couple things starting on VFDs, but does everybody understand the basics of a variable frequency drive, how it works, what it does? If you don't, kindly raise your hand, nobody else look around, see if we want to start at the very basics of what a VFD is and what it does for us. And after that, Paul's going to go into the bypass aspects of things, so we'll talk about bypass in a few minutes. I'll ask that same question again. Okay, so why do we use a VFD first and foremost? It's this magic black box that controls a motor speed, right? But why do we use it? It's one of those things that's come so common in the last 20 years with how VFDs have proliferated in pretty much every motor on an HVAC system and other systems as well, that we kind of forget all the things that it gives us. Primarily, it all comes down to money. We're doing it to save money, but we're doing it because we're reducing the maintenance and we're reducing the energy consumption of the drive. That's probably the big one. We're saving the energy by slowing the motors down. But all of these things get advantages that we can do on a VFD-driven system that we couldn't do if we were just across the line. So how do we save the money on a VFD? Well, essentially, this is mostly related to HVAC applications. This is fans and pumps. There's a mechanical law about how fans and pumps operate. It's called the affinity laws or the fan laws. And it relates to how power is consumed using a fan or a pump, and it's not a linear relationship. So if you notice, this curve goes up pretty fast in the speed that you go on the motor, and that's equal to the flow. So how fast you're getting flow of the pump or of the fan and the energy you consume. So 100% speed, 100% flow gets you 100% of the horsepower. All right, pretty straightforward. But if you can reduce the speed just a little bit, you see that the energy just drops off a lot faster than linear. So with the affinity laws, we can save a lot of energy by slowing down the flow rate of the VFD and slowing the flow rate of your system down just a little bit. So this is a nice pretty chart. It shows something, but it works a lot better, it seems, in tabular form if I actually go to producing that same chart in a table for you and highlighting a couple things, like at 80% flow, 80% speed. So if we've taken a fan and we've slowed it down to just 80%, and that's, a common day. That's not, you design these systems for your 105-degree days here in Kansas City, but that only happens 3 or 4 days a year. So if we're normally operating here, say 80% flow and speed, that's not 80% of the energy you're consuming, it's only 50% of the energy you're using. And 50% flow, where people think, well, if I'm slowed down to 50%, that'd be half my energy, right? No, because of the way that energy consumption works in a fan and a pump, you're actually at 12.5% of your energy at that point. So we reduced in this example, a 120 amp motor down to 30 amps by going half speed. There's a huge amount of energy savings you can get on these things, so therefore a huge payback by being able to take an existing motor or a new design system that you've got a VFD and deciding to slow that motor down. You can't slow the motor down across the line. There's no way to make that motor go slower when you've got 6 hertz power coming in. You need something in front of it to be able to change the frequency to the motor, a variable frequency drive to change the frequency. That in turn changes the speed. So far so good? All right, so what is a variable frequency drive? They're these magic black boxes, right? Or in this case, magic white boxes that sit on the wall. And they hook between the three-phase power coming in to the motor, three-phase out to the motor. All variable frequency drives run three-phase motors. They can run on three-phase power coming in nominally, but they could also run on single-phase power. And Paul's going to talk about some single-phase issues that are coming up soon too. But primarily what it is it replaces the idea of a starter. You know, a lot of times people put that in their head. They had a starter in somewhere before, now we do VFDs instead of starters on these systems. And the VFD changes the speed of the motor by varying that frequency. So internally, electrically designed, what's the inside the guts of a VFD? This is an electrical diagram of any VFD that's out there on the market now of a standard six-pulse VFDs. What it entails is there's 3 sections to a modern VFD. You've got the input bridge, the diode bridge converter section of the drive. You've got a DC bus or energy storage portion of the drive. And then you've got this output section or IGBTs or inverter section of the drive. And that's where the transistors inside the drive, the magic of the drive, turns on and off power and sends it out to the motor. So these 3 sections of the drive take AC power coming in here on this 3-phase incoming power, 208, 460. Take 3-phase, we run it through this converter, this input converter, these diodes that take all that energy and store it in a big DC bus inside the drive. Now on a 480 volt system, that's 650 volts DC stored inside the drive. So you've got this big 360 volts DC energy source, and then we have to take it and chop it up on and off and on and off on these transistors and send power out to the motor in a chopped up DC form that when the motor gets it, approximates a sine wave. So it approximates the power that the motor was expecting to see in a sine wave fashion anyways. Why do we go to all the trouble to take AC, turn it to DC, just to turn it back to AC? Anybody got an idea? So we can slow it down, because there's no way to actually change the frequency of power coming from the utility company, but we can change the frequency by using these transistors here, and by changing the frequency we send to the motor, we slow the speed down. So I've got a different presentation here for a second. That puts it in a lot more layman's terms. All right, so here we are again. It's that same kind of idea of a picture. You get 3-phase power coming in from the utility. We rectify it or turn it from AC to DC in the diodes. We store it in the DC bus energy, and then we invert it and send it back out as a sine wave. So 60 hertz power comes in. Any frequency we want can come out of the VFD. The VFDs today go up to 600 hertz. Not that most of the fans and the pumps are ready to do that, but the VFD has more capabilities for speed than the equipment that we're driving.
Hey, Rich, if I may, real quick. A typical motor in an HVAC system is going to be a 60 hertz motor. So at 30 hertz operation, you'll be running at half speed. So I just wanted to make sure that everybody understands when he's talking frequency, that he's talking about the base frequency of the motor.
Question?
So to that diagram, if you took 230 volts single phase, you could run a 3-phase motor.
Absolutely. The question was, if we were to take in 230 volt single phase power coming in here, could we run a 3-phase motor here? Yes. Most modern VFDs are set up to be able to take in single-phase power and spit out 3-phase power. Sometimes you have to choose a specific single-phase only incoming power VFD. All the ABB drives here that are rated for 208 volt 3-phase incoming power are also rated for a single-phase operation. So you just omit one of the wires and you bring in two hot wires instead of 3 for running single-phase into the drive, and then it will always spit out 3-phase to a 3-phase motor. That's a good point that the VFDs in the modern world right now, they're all running 3-phase motors. There aren't very many manufacturers of single-phase motor VFDs because it's kind of hard to make a single-phase motor spin the proper direction using a VFD technology. 3-phase gives you the ability to control the speed, but single-phase out is a very small market and most VFD manufacturers don't play there. no problem bringing single phase in, but we're always running 3-phase motors.
Rich, you want to talk about single phase and what you have to do when you select the drive?
Yep. So on the ABB drive, which you can take this 10 horsepower VFD, 208 volt, 3-phase 10 horsepower VFD. If you want to run a 10 horsepower motor, but you only have single phase power coming in, you have to take the 10 horsepower VFD and turn it into a 20 horsepower VFD. You have to derate the drive by half of its current, because on this side, the power coming in, this thing's rated for 10 horsepower at 3-phase power. That's 30 amps essentially. We've got essentially a section here that's ready for 30 amps, but if you take away one of those legs, it still can only handle 30 amps, so it's only going to be able to produce 15 amps on the output side. So that's why you double the size of the drive so that this side can handle all the amperage necessary to give you the power you want out there. So you'd end up with a 10 horsepower motor, 20 horsepower VFD, and single phase power coming in, and it would work just fine. So layman's terms, how does the VFD actually turn on and off power going out to the motor? So remember the diagram we had before, we had the 3-phase power coming in, we converted to DC, I omitted all that, and now we've just got DC here. We've got 650 volts DC power here on this side of the drive. And now the transistors, those IGBTs, or the inverter section of the drive, I'm approximating them as a switch, because essentially that's what they are. They're a very fast electronic switch, but essentially it's kind of like a light switch, on, off power. So every time we turn on a transistor, it conducts an electricity to the positive side, and we send out a pulse of energy to the motor. And then we turn it off again, and it goes back to 0. Then we turn it on again, and it goes to, on the negative side, and we go to negative voltage, and off again, back to 0, on again, off again. So that sort of approximates a sine wave when we get done. In reality, it does it thousands of times a second, and it does the same switch on and again, on again, on again, on again on one side. And then when we get wide enough, you'll notice the pulses are getting wider. That's the pulsed width modulation. That is part of a VFD. Turn on and off thousands of times a second on one side, and then we do it again on the negative side. Thousands of times a second on this way, thousands of times a second on this way, and when you're done, it kind of looks like a sine wave to the motor. And the motor is not smart enough to see the difference, and it says, oh, all those DC pulses, I'm going to say that makes me run at a certain frequency. How fast we do that is the frequency that the sine wave comes out of the thing. So thousands times a second, on and again, off again, but it's how many times we transition from on to off that determines how fast the frequency is on this guy. So if you look, you'll see a 30 hertz or half speed signal. The pulses are widely spaced, but on a 60 hertz full speed signal, the pulses get closer together. So you get more on again, off again cycles in a second. So by varying that frequency, we then change the speed that the motor goes. By changing the speed the motor goes, we can actually affect the energy draw that the fan or the pump requires on it and save ourselves a bunch of electricity. So now take that from one switch and turn it into the 6 transistors to the 3 phase of the motor, and you end up with this fun little pattern of on again, off agains that send the power out to the motor, and it is the magic of how a VFD actually does its job. So questions on the basics of how a VFD actually sends power out to the motor? Yes, sir?
How does that affect the life of the motor?
Okay, so the question is, how does the on again, off again cycling affect the life of the motor? The answer is, it depends question, right? So there's no simple, easy answer on it, but it can have detrimental effects to the motor. Those on again, off again pulses, they're at 650 volts, but actually the transition times to make them go on again, off again means we have overshoot voltages.
There's no moving parts. Those aren't mechanical.
No moving parts, not mechanical switches. These are electronic switches inside. So if you have a long cable distance between the VFD and the motor, you have a higher chance that those on again, off again switches are going to start degrading the insulation of the motor. If you have a really old motor, and now I'm talking 20 plus years old motor, the insulation in that motor probably wasn't rated for the voltages that a VFD could produce. The quality of a VFD can affect the, the componentry inside the VFD, and the manufacturer's concessions on cost versus benefits may mean that you have higher voltage spikes to the motor than a different VFD that might have had higher quality componentry. So all of these things come into play, but ultimately those spikes have only one way of damaging a motor, and that's damaging the insulation of the motor, which would always manifest itself as a turn-to-turn fault. And usually you're in that first turn of the motor, so you'd end up with a phase-to-phase short. You go measure your system, you end up with a, oh, these two phases are dead shorted to each other. That's the fault that happens if a VFD is going to kill it. The symptom oftentimes would manifest itself in a situation where you had a new installation, and 3 months later the motor seems to be dead. Okay, replace the motor. 3 months again, it happens again. So if you have a reoccurring issue where a VFD and a motor aren't playing nice and the motor keeps failing, you might look at the VFD as a possible cause of that. Usually that is when you've got really long cable distances. And really long in the industry is anywhere between 100 to 300 feet. Ours are 300 feet distance rated, where we can go 300 feet of distance before we have to really worry about that motor, but that's not true for all VFDs. There are other things that VFDs don't play nice with motors on, but that's the majority of how those pulses could affect a motor in terms of its lifespan.
Rich, another thing to take into consideration is if you're trying to develop a specification for your motor manufacturers, make sure you specify a NEMA MG1 Part 31 motor. And that's going to give you 1600 peak volt windings. You know, Richard talked about 650 volts DC being pulsed to the motor. Well, we get something that's called reflective wave voltages. We can get reflections of that 650 volts back towards the drive. And when the 650 volts meet in the middle, they essentially can double. And because of some of the overshoot issues, they could actually more than double. We won't get into that unless you guys want to dig deeper. But a 1600 peak volt motor is going to protect you for some pretty significant distances. And it's going to allow your motor to live longer. And most motor manufacturers today, their standard windings are rated for 1600 peak volts. Yes, sir?
The question is there certain motors that can't be used on VFDs because of the bearings? I would say not necessarily because of the bearings, but there are instances where a VFD could be contributing to the demise of the bearings. We could be killing the bearings with the VFD. It's a more rare phenomena than most of the symptoms that a VFD can do, but it's not as rare as the VFD manufacturers would like to have thought 5 years ago. That's an ongoing education process. It's something called electric discharge machining or bearing currents. And if you want to go into that, we can happily go into all that we know about that. But that's a learning experience where we're all in the industry trying to learn exactly when that happens and how to prevent it. We've got great knowledge, but it's not complete yet.
There are technologies that you can add to your motor to prevent that from happening. There's a lot of different shaft grounding solutions out there, shaft grounding rings, carbon brushes that are spring-loaded that allow the shaft to leak that current and voltage back to ground and back to the VFD. So we can get into that either later in the discussion or afterwards. If we don't cover it adequately, let us know and we'll get into it in great detail.
Good with VFDs in general so far? Because we're going to get Paul up here next and we're going to talk about VFDs and the bypass. So I've done a simple illustration of a vertical VFD and bypass. We've got one sitting over here on the bench, but you'll notice the top portion is still just a VFD, just like those pictures I showed earlier. The bottom portion is the bypass section. So you notice you end up with a VFD and now extra stuff on here. The bypass being the redundant path of power to the motor. It's the backup to the VFD. In case that VFD fails, you want to have some way of providing power to that motor, even if it is just an across-the-line starter, which is essentially the guts of what all bypasses, regardless of manufacturers, are. They're still just a three-phase contactor pulling in to apply power directly to that motor. So a drive and a bypass is something that we have been using for 20-plus years, though there are advantages and disadvantages that Paul's going to talk to, as well as the evolution of how it's grown.
Thanks, Rich. So, we're going to do some whiteboard stuff here for a little bit. We'll get some more light turned on here. Get everybody woke up after their lunch. Okay. So, everybody understands, Richard talked a lot about the drive. Back in the 80s, failure rates on drives were very, very high. The percentages, drives were new technology. The componentry wasn't there, wasn't mature enough yet. So we had a very high failure rate. I mean, so much to the point to where in my early days when I would go to install a VFD or service a drive, I would bring a spare with me. The failure rates were that high. Today, most drive manufacturers are seeing an in-warranty failure rate of about 1 in 2,500. So the reason we added bypasses in the 80s was because when we had that failure, that high failure rate, we needed to have the ability to route power around the VFD. And a hard start, you know, if the drive, you get a nice smooth acceleration and we're saving energy. But if something were to happen to that energy savings device, we needed to be able to route power around the VFD. And that's what the bypass is for. We put some contactors in there, and I'll talk about that a little bit more in a minute. So really what I want you to think about today is, today still 80% of the drives we sell have bypasses on them. But with these kind of failure rates, if you don't have a supercritical application, do you really need to have a bypass? So we're going to talk a little bit about that. Because what happens is when we start adding additional control to the drive, we're now making the drive and bypass system as a whole less reliable. And I'll get into why that is. We're adding components, we're adding points of failure. So if the drive's very, very good and is unlikely to fail and you don't have an ultra critical application, does it really make sense to have a bypass? So we'll start with that. This is a drawing, a three-phase drawing of just a VFD with no bypass on the wall in your mechanical room. Anybody have an idea of what the voltage tolerance that a drive on the wall without a bypass has today? So you all have perfect power in your buildings, right? No brownouts? No single phase scenarios where you get a single phase for a short period of time? Nobody's burning up contactors, no contactor failures. We've all seen them, we all have them. So what a VFD on the wall can do is it has a voltage tolerance of plus 30, minus 35%. So that's a big voltage tolerance. So keep that in mind as we move forward. We also, as Richard talked about, can lose a phase and still operate the motor, amazingly enough, without a bypass. We had a bypass, it's a different story. We'll go into that in a minute. So add that phase back in there. So what is a bypass? A bypass is, like I said, we're going to route power around. So back in the 80s, we came up with this really crude practice of what's called a three-contactor bypass. There's a drive isolation contactor, a VFD output contactor, and then what's called your bypass contactor. What we're doing essentially, as I said before, is routing power around the VFD in case of an emergency. So this contactor is pulled in when the drive operation is running. This contactor is pulled in when we're in bypass mode. And this contactor originally was put here to isolate power from the input of the VFD so a service tech could work on the drive. That's a three-contactor bypass. Well, NEC number 1 doesn't approve of allowing a contactor to be an electrical barrier for someone working on a device. So the three-contactor bypass quickly kind of went away. So now most manufacturers manufacture what's called a two-contactor bypass. And there's just these two. Only one of them can be pulled in at any given time. If this contactor is pulled into the VFD and this one, we backfeed AC power from the utility into the DC side of the drive and blow it up. That's why it's important to have these two contactors here. We're protecting the output side of the drive from line power, okay? So that's kind of how it evolved from three-contactor to two-contactor. Now, people still wanted to have a sense of security, so drive manufacturers added an optional service isolation switch to the front end of VFDs. But what they really neglected to do was add another one down here below. Because if you can kill yourself here, you can kill yourself here too, right? If you're working on this device and we have it in bypass, there's 480 volts right here. If you accidentally bump the plunger on that contactor, you can send AC voltage into the DC side of the drive and you can kill yourself. It'll blow up in your face. So really, it's a false sense of security adding that service switch inside of the box. You still want to have the main service disconnect switch, which is on the outside of the box. Richard, will you point to that? That kills power to the entire box, with the exception of where power hits the line side of that disconnect. So that's really how it's evolved. So it went from a three-contactor to a two-contactor. The other thing that happened is when there was a critical failure in the VFD, a capacitor failure, just something critical internal to the drive, what would happen? Where would we clear fusing? It would clear it at the branch circuit device. That might be in another room, another building. So now the drive fails, we clear the switchgear breaker, and now we've got to find that breaker somewhere in the building in order to go to bypass. Well, that was a problem. If somebody's on an operating room table and we're trying to maintain positive pressure, we want to be able to get to bypass quickly. So what the drive manufacturers have done is they've added fast-acting drive isolation fuses ahead of the VFD. And their main purpose is to clear in the event that there's a critical drive fault. They'll clear prior to branch circuit clearing. Now we have a drive failure, and we can manually switch to bypass without going and resetting the branch circuit. So that was a very important step in the evolution of the bypass. So we move forward. Poor power quality issues are always a problem, and what do we have? We have contactor issues. Anybody know how these control power contactors are powered? Anybody? Do we use the 480 volt to power these? We don't. We use 120 volt or 24 volts. We do that with a control power transformer by taking 2 of the 3 phases and converting 480 volts to 115 volts and powering the coil pickups in these contactors. Remember, we said that this drive by itself on the wall was rated for plus 30, minus 35% voltage tolerance. Anybody know what the voltage tolerance is on a control power transformer? Plus or minus 10%. So we've now taken a device, added control around it, and made it less reliable. What happens is, if we get a voltage drop of more than 50 volts, we don't have enough power to keep these contactors pulled in, so they drop out. But the building management system is saying, no, we need flow. Move the water, move the air. So they pull back in. They drop out and pull back in 150, 200 times in a minute, and it burns up the contactor. Okay, so now we're out there with a service call, changing those out. Any questions on that? Okay, so what do we do about it? Am I going too high level? Am I okay? Okay. So what do we do about it? Well, we went to a dedicated power supply. We've got rid of the control power transformer. We put a switch mode power supply in here. And we now take power off of all 3 phases. And we now have plus 30 of 600 volts, minus 35 of 200 volts voltage tolerance on our contactors.
Here's where I like to say, what is this switch mode power supply he's talking about? It's a fancy verbiage, right? It's an electronic box in there and one more stuff, right? But it's more stuff that we're all very familiar with. This is a switch mode power supply. This has been running my laptop for the last 3 years. Nobody gives a second thought to these guys. If you look at it, it can have a range of anywhere from 240 volts to 110 volts, and it always spits out the same voltage to keep my power on the laptop working. We did the same thing, just on a higher grade, higher level, much more industrial, rugged componentry to take in 480 volts or 208 volt and always spit out 110 to the contactors. So by doing that, we have a wide range of voltage acceptability, just like this thing does. So instead of having a simple control power transformer that was fluctuating in the power it would send out and therefore causing contactor failures, we've replaced it with something that we're all very familiar with and is very reliable as a switch mode power supply, regulated power supply. This has become the industry standard for VFD contactor pull-in, whether it's a 24 volt output DC or 110 volt like what we've got going out to AC contactors. You'll find most of your VFD bypasses nowadays are using this instead of a control power transformer.
So that's how really the bypass has evolved. I mean, we had the VFD, very reliable issues. We increased those. The VFD is much more reliable now. Then we had this bypass, and it was really decreasing the uptime of the VFDs. So we fixed that problem now as well. But it's still about return on investment. You as the owners are investing in this equipment, and the question is this acceptable in your environment? If it is, don't add all of this stuff. I mean, I want to sell equipment. I'm a rep. I sell mechanical equipment. I'd love to sell you bypasses. But the responsible thing for us to do is to explain to you that based on these failure rates, and if you're in a general office building, by the way, we stock and our competitors stock VFDs. You know, we stock fractional through 100 horsepower, and Design Mechanical picks up drives from us all the time out of our inventory. So it's not like if a drive goes down, you're waiting months. It used to be that way. In the 80s, if you ordered a drive on January 1st, you wouldn't see it till the middle of February. And a 5 horsepower drive was the size of that door. Today, a 5 horsepower drive is that. That's a drive and bypass at 5 horsepower. So we stock these things, they're immediately available. Downtime is very short. So just important to think through as you're investing, because really it's about how long it's going to take to get payback analysis on this piece of equipment. So how do we improve it further? your buildings all talk, for the most part, some sort of building automation, BACnet, Johnson, Siemens, whatever it may be. And VFDs for a long time have communicated back out to the building automation system, right? I mean, they just have for many, many years. Probably early 90s was the first Siemens system we put in. Right. ABB was the first with Siemens, first with BACnet, first with Johnson, first with Modbus capabilities. So what we've done now is we've added all those capabilities to the bypass as well. Why that's important is if you have a drive failure and the drive needs to be removed from the system, we can still operate in bypass, and we now can also communicate to your building automation system, let you know that you're in bypass, that you're no longer saving energy. It's running full speed. You don't have variable flow. So we have a lot of capabilities built into the systems that are far beyond what they were 10 or 15 years ago. So that's a drive and a bypass in the history of bypass. So what's our next topic, Rich?
One more thing about bypass.
Please, yes, questions about
What I've
bypass.
seen some people do, and I'm curious what you think of it, is if it's a retrofit and they've got an existing motor starter, they'll mount the drive next to it and route through the motor starter, but they'll leave the starter there in case, and they don't buy bypass. So if they ever have to switch over until they get another drive, they will hit the disconnect and switch the lead back over. I mean, what do you think of that?
It's not bad. It's the first bypasses were exactly that. You know, that's exactly what happened. There was an existing motor starter. They added the VFD, but didn't take out the motor starter because they didn't trust that fancy piece of electronics. So that's exactly what happens. The only problem with a bypass of that magnitude is that you still have to have a lot of manual intervention to get the VFD to transfer to bypass mode. So if you have a failure of the VFD, did you have the correct branch circuit protection between the VFD and the bypass so that when the VFD failed, that the bypass still has power? Because if you don't have that, if you don't have those fuses that Paul talked about, well, then your bypass doesn't have power either because the branch circuit protection downstream is, or upstream is what tripped. And so there's nothing to click over to bypass because the power has been turned off. So there are lots of things that have evolved through the steps to make the bypass more redundant, more automatic, more reliable than in the past. But by all means, leave your starter there as long as they're willing to accept the, okay, it's not that critical, we'll come over here, we'll flip these two switches, and then we'll send power to the motor via a start-stop signal that hopefully still will land into that instead of having to then take those control wires off the VFD and land them back again into your starter.
The other thing we're seeing a lot more of is customers don't want that constant speed bypass. So that stainless steel NEMA 3R outdoor enclosure there is a redundant drive package. And it's exactly what we've been talking about. It's really everything that a bypass is, except for there's a VFD backing up the VFD. So if this drive fails for whatever reason, we auto transfer to the second drive, take care of the problem here, reset it, and it auto transfers back. You can decide which drive is the lead. You can even set that up so one drive is the lead 1 month, another drive is the lead the other month, so we put the common share time on the VFDs for runtime. So that's a redundant drive package, and we're seeing much more of that. We're also seeing much more frequently where we're operating multiple motors on the output of a VFD, and that can be done as well. We don't have to just run one drive with one motor. If we have a cooling tower with 3 cells and 3 identical motors, we can size that VFD to operate all those motors. Now they're all going to ramp up and down together, but guess what? Richard went through the affinity laws earlier. 2 cooling towers running at 50% speed is way more efficient than 1 cell running at 100% speed. So if we ramp these up and down together, we're going to see significant energy savings. So just some things that are new in technology.
When you're running multiple motors off of VFD,
Mm-hmm.
is there a way through the VFD to cut out one of the motors, or does that have to be done with
The question was, if you're running multiple motors on one VFD, is there a way to cut out or eliminate one motor from the system? And the answer is yes. It's been fairly well thought out. It's a fairly mechanical solution. You can actually see it here. This is a redundant VFD solution, but it could have been one VFD instead. But you'll see down here I've got 3 motor manual circuit protections going on here. So each motor has its own overload protection. And in this case, it also has a automatically tripping device, a manual motor protector that turns off. If that one motor starts to overamp, it'll shut that one off, leaving the other 2 to run. You could also come in and manually do it by hand if you'd like and turn off that one motor so that when that one's down, for whatever reason you want to maintain that cell or that pump or something, you don't have power going out to that guy. So it's something we do quite often. But you got to have protection in there. Yeah, you got to protect each motor.
What happens if you have multiple motors is the drive sees the multiple motors, the combination of motors, as one load. So if you have 3 10-amp motors, that's 30 amps of load. But the drive has no way to know what amp draw is coming from each individual motor. So if you're running at a very slow speed, one motor could be overamping and the drive wouldn't recognize it because it sees it as a single load. So we put those overload protection devices on the output of the drive between the drive and the motor so that in the event one motor goes high on current, it's going to fail. It'll trip off. That thermal overload device will be there so that we don't cause a fire or burn something up in the building. So that's how that works.
Do that through the automation system?
You can. We prefer, if you want to operate multiple motors, that we put a drive on every motor. The reason we want to do that is likely if you have a fan array, for example, with multiple motors in a single air tunnel. If you have one VFD and one of those motors goes to ground, the drive is going to trip on ground fault before those thermal overload devices can detect it. So then your whole system will go down. So what we do is we do a multiple drive cabinet where we put a drive on every motor, a little micro drive. And then if one motor goes to ground, that one drive trips. It doesn't take down the entire fan array. So we use an inexpensive shaft turner drive device on every motor rather than an expensive drive that we apply to all the motors in that case. So does that make sense? Okay, good.
Well, Paul, what's a ballpark 5 horsepower drive with bypass compared to 2 drives?
Yeah.
Does that cost twice as much as a drive?
Well, what you'll see is the drive's one cost, right? Then we have the adder for the drive and the bypass. And through about 30 horsepower, the drive and the bypass are about the same price. And in a redundant drive package, we're adding another drive. So 1 plus the bypass plus another drive, right? So there's some cost to that. This is one price. This doubles it, and this triples it.
Right, but what I'm asking is if I had a 5 horsepower drive only,
Yep,
and I add the bypass to it,
double.
so it's double, so I could almost buy two drives for about the same
You
price.
could, but then you still have to buy all the same components in a bypass. Yep, absolutely.
So if you had 2 motors and 2 pumps, and then you decided at 5 horsepower motor, do I put a drive and a bypass and I separate that one to go to both motors, or do I buy 2 little VFDs? Buy 2 little VFDs. You've already redundant motored and you've already redundant pumps, so why would you then need a redundant VFD and bypass for each of those? No, just buy a simple VFD only at that point.
And if there's not more questions on this, Richard's going to move on. I know we're getting short on time, so we want to keep moving here. Richard's going to talk about planned obsolescence and life cycle management. We want to talk about how long these devices should last and how you can proactively plan to make sure that you're changing them out at a rate that doesn't become inconvenient for you. So that'll be the next topic.
So a couple months ago, I think it was nearly 6 months ago, I was talking to the facilities guys at one of the large universities in Kansas, and we were talking about VFDs, and it came up that they didn't really know what VFDs they had on campus. They knew they had a lot, and they'd been getting them on projects a lot for the last 5, 6 years, but they didn't really have a good system of tracking their VFDs or their mechanical equipment, and they wanted to improve that. They wanted to change their maintenance from a reactive maintenance system into a more proactive maintenance idea. So they asked me to come in and tromp around all the mechanical rooms and write down every VFD they had on campus. And there were over 200 that we found, and I gave up after like 3 days. I'm sure we got about 85% of them. But they were trying to, in fact, get a 20-year maintenance plan going. They were trying to predict for 20 years what are they going to need to have for cost structures for maintenance. And I thought that was a brilliant idea. Let's figure out what we're going to be and needing to be so we can proactively predict what we're going to have to replace at certain times. You ask any manufacturer of any piece of equipment, they'll have an idea how long that piece of equipment is going to last. Everything wears out, right? So I went and inventoried the VFDs. I went and wrote down the age, the manufacturer, their volts, amps, hertz, whether it had a bypass or not, and gave them a suggested replacement for each of the VFDs on campus. Created a nice pretty report with lots of spreadsheets so they'd have some way of tracking their equipment by the mechanical room in this building, in this mechanical room, running this piece of equipment. They'd know what they'd have and be able to use it from that point forward. So with the 20-year maintenance plan that they wanted, we came up with through multiple conversations, I knew most of this from working at ABB, how long does a VFD last? It's an electronic piece of equipment that we're expecting is going to have about a 15-year usable life. And when you break it down, we're expecting actually 50% of the VFDs to fail by their 20th birthday, and 10% of the VFDs to fail at their 10th birthday. So that's just a rough generic VFD kind of idea of the failure rates of VFDs. And with that and knowing the age of your equipment, you could then start budgeting for replacement. You could then get it into next year's budget. Say, I've got 10 VFDs that are somewhere between 12 years and 15 years old. We're going to have a certain number of those that are going to have to be replaced. So this is a resultant chart of that university's VFDs. And you'll notice that it's age in years on the bottom and the number of VFDs they have for that age. Most of their VFDs are in the 0 to 6 year range. That's because they've done lots and lots of projects recently, and everything comes with a VFD. Now, if you go out to 25 years old, nobody's putting VFDs on anything 25 years ago, so there weren't many out there. They do have some that are 24 to 29 years old, and those are the workhorses that have just been out there forever and the anomalies. Here's the area where we're expecting that we're probably going to start working on replacement ideas. We've got the 12 years to 21 year range, and they've got multiple VFDs in there that we're going to start worrying about. You know, the 6 to 9 years, no, those are still in their usable lifespan. 9 to 12, sure, we're not going to have too much going on here, 10% in this 10-year range. But it's the 12 years, 15 years, 20 years lifespan that these are the ones we're expecting we're going to have to replace. You take the total number of count, in this case it was like 35 drives they had in that range window, and expect that half of them are going to be needed to be budgeted for next year. That doesn't mean you go proactively replace them unless you actually wanted to proactively replace them and not have to do it on a Sunday at 2 in the afternoon kind of thing. But for the most part, they were able to get a budget going of these 30-some drives that they could put together and say, this is how much we're going to need for VFD replacement in a year. Well, as soon as you tell somebody that their stuff's going to break in a couple of years, they start wondering, did we get our lifespan out of that? Did we get our use out of this thing? And I asked them, well, these are electronic pieces of equipment. This is a 15-year-old piece of electronic equipment. This is the stuff that you can no longer buy that was around at the time those 15-year-old VFDs were around. Anybody carrying around a bag phone still? Or have a CRT monitor on their computer anymore? Or a Walkman that they carry? This is the kind of stuff of how technology marches on. VFDs are a little slower paced in the technology because they're not the consumer level of instantaneous changes. They're much more reliable pieces of equipment that don't get so flashy and fancy. But the end result is that we had to put in some calculations. What does that VFD save you? How much energy did that VFD save? How much cost has it not cost you by having a VFD? So I put a simple calculation together for in this case, a 75 horsepower VFD. And a 75 horsepower VFD roughly costs $8,000 to $10,000 to put in. That's installed cost for a VFD, conduit, buying the equipment, paying somebody to put it all together, program it, about 8 to 10 grand. Well, over the span of 15 years, if we're using 15 years as its lifespan, and if we're being conservative, running only 10 hours a day, 5 days a week, because we're talking office building kind of stuff, how much did that energy savings cost you, and how much did it save you? Well, eventually I could have done the cost and give you the numbers of how much electricity is used, but if we'd have run that motor across the line compared to a VFD, the difference in cost there was $250,000. So in a way you could say the VFD has saved you $250,000 in the course of 15 years, and you could say thank you at the end of 15 years, buy another one for 10 grand and realize that every year you're going to save again another $25,000 or another $20,000 of electricity by having that VFD instead of not having it.
Now, Richard, is that based on ASHRAE duty cycle?
Yeah, this is an ASHRAE duty cycle of a estimated time of running for a office building that, at 60% of the time it's going to run, I'm sorry, 23% of the time it's going to run 60% load, but only 3% of the time is it actually going to run at 100% speed. So there's a time of speed variation that's based on. So that was the end of my life cycle analysis stuff, and it was actually, quite informative. It was nice to have a facilities guys that cared enough to do that ahead of time and put these sort of efforts in it. Questions on life cycle VFDs?
If you're running more than 10 hours a day, does that shorten your life?
Oh yeah. Yeah, so the question was, if you're running more than 10 hours a day, does it shorten the life? I'm sorry, I answered yes before I thought about the question. If you're running more than 10 hours a day, it reduces the dollar amount that you save, but it doesn't actually shorten the life of the VFD. VFD lifespans are mostly limited by their electrolytic capacitors that are inside the VFD. So the electrolytic capacitors have a usable lifespan, whether they're being used lightly or being used heavily, or being used 20 hours a day or 10 hours a day. They have a fixed lifespan that they're going to be enduring, and it's usually in the 15-year mark. So more hours a day may have a lower may lower the expectance of the drive's ability to be used. Maybe shortens it a little bit, but not by a substantial amount that anybody's tracked.
Another thing that greatly affects the payback is making sure you select a service organization that's trained on the products. It's very, very important. It can take somebody who's not trained, it could take them an entire day to start a VFD. Someone who is trained, it should take a couple of hours to do a startup and commissioning. That doesn't include the install time, but the point is that it's very, very critical to make sure from a labor standpoint in your payback that you're selecting an organization that's trained and ready to do that and does it on a frequent basis. So the building you're in, most of their service techs are trained very, very well and have been through lots of training. So I just wanted to throw that out there. I think that's, unless there's questions, we want to talk about other topics, we can stay as late as you'd like. We'll turn it back over to you, Valerie, and you can kind of manage that.
All right, thank you guys for doing it.
Thank you.